Thank you very much. Dobre dan, gosti. Dobre dan, colegi. Unfortunately, that's where my Slovenian stops. So I have to do this in English, so I hope you bear with me. If I speak too slow or too fast, please raise your hand, right? Because sometimes I have 45 minutes with you, and I'm always excited to tell a lot of stories, but I have to make sure you can still follow me, right? And it's not your native language, of course. So before I start, do we have any quantum experts in the room here? Anybody study quantum physics? No? Okay, that's good. Otherwise, if you know everything about quantum, you can jump on me, ask me questions, because I want to take you to a bit of a journey today. And I want to talk about the future of AI and quantum. And I hope 10 days from now on, you will look back at this day and you think, hey, this is actually the day where I really got in touch with quantum and, the combination with AI. At that time, I didn't know so much about it. But then I really started realizing the impact that it had, actually. And now it's so normal because, it's almost a daily discussion, right? So let's sit here together 10 years again, see where we are at that time, okay? So, I was already introduced, so let's not talk about that. But let me go through the story right away. When we talk about a lot of new technologies that we'll talk about, AI, quantum, cloud, we also have to realize this sort of stuff was not around forever, right? If you look back a couple of hundreds of years, we were at the agriculture age, right? Yeah, we had nothing like computers. Then we came into the machine age, and it became much more normal to have machines, industrial production, but also have paper, all those kind of things, right? So where we are now is what I call the smart machine age. Smart machine age is a bit of the next step on the second machine age. And maybe you have read that book on the second machine age, but I think actually it's about being smart. Everything is becoming smart. Companies are becoming smart, robots are becoming smart, and you can see that in everything around us. But it's not just about being smart, it's also that companies nowadays also need to be smart companies as well. And you see a bit of the little logo here around the SDGs. It also means that actually purpose is also becoming very important. And what I would like to talk about today is also how you can actually connect purpose, AI and quantum, right? What you will see is I will do a bit of an overview on some of the topics, and I will go very deep in some of the other topics. So please stay with me for the coming 45 minutes, okay? When I talk about smart companies, it's also about purpose, like I said before. So yeah, what you actually see is that it's not just about stakeholders anymore of companies, right? It's important to also have a sort of purpose as a company, right? That you're doing something for society. And it's also what you see here on the left, social value, and on the other side, the customer value as well. Part of that is actually using technology to become a smart company, right? So actually, we are now in a time where we can start using new emerging technologies to actually be better on those kind of things. When I talk about purpose and sustainability goals and so on, this is the list. Maybe some of you are aware of this already, but this is used in Europe from the EU, the different goals that we have, sustainability goals, right? And I will just use one of them, a bit of an example. You see it here, number 3, around health, right? So I will use actually how you can connect these SDGs also, and this purpose also to these technologies. Why are we in the smart machine age? What we have seen the last years is, of course, we had a lot of technology that has been developed. But now we are at a time where 3 things are coming together. AI gets to a maturity level that we can actually use this in a lot of different disciplines. The other thing is unlimited computing power, right? We already have cloud, of course, that's growing, and a lot of companies are adopting cloud. Of course, we have supercomputers, we have the edge already, but what we will also see is a new technology that we call quantum, right? And at the end, that's not going to replace the other technologies, but it will get a part of the overall computing power that we will have. And if you have unlimited computing power, you can actually use this AI and improve it. What we also see is that a lot of data is now digital. And that means you can actually use all that digital data to train your AI. And that's very important to actually make the next step, right? Maybe you have seen all these things on the internet that we try to recognize a cat with AI. Well, that's a good example. If you train that, you give it millions of cats, you will see it will be better to actually recognize a cat. So technology is the driving force in the machine age, in the smart machine age. But of course, around that, it's not just about emerging technologies, but you also need to make sure that you are secure and that you have the cybersecurity in place and that everything stays connected. But because you will see that you need to have connections between all of this to actually make this work. What I said, computer power, very much about cloud, quantum computers and the edge. If you look at AI, you see a lot of different components, and I will come into that. And digital data, everything is becoming digital, so we can actually use it for training of these AIs as well. If you look at the development of AI, we see actually over the years a lot of achievements, right? We have even vacuum cleaners that go around the house, you know, vacuum clean them themselves, and they learn actually about the room and where they have to go and what the pattern was, right? But recently, you also see that on Stanford, for example, there are also some breakthroughs actually on recognition of handwriting. Yeah? So we are getting to a point that some of these components are becoming so smart they are outperforming humans. What is actually an AI? That's maybe a good thing to start with. And a lot of people think if we talk about AI that there will be a sort of super person, maybe her, right? That looks like a human, is very smart, you can talk to her, you know, she can walk around, she can do things, you know, like any other human. But of course better, because it's an AI, right? In reality, maybe it looks a bit different, yeah? But let's look at that, how that actually looks really. The question is also what makes actually a human real, or what makes an AI? Yeah? When are you an AI? If you have supporting AI functions, for example, if we put the glasses on, that we are smarter, right? Or that we can see things better, or that we can recognize or scan stuff, are we an AI then? Or yeah? When are you an AI and when are you a human? I would like to do a little test with you guys. So when do you, what makes a human actually real? And I would like you to vote. And you can't stay out of the voting. Either you put your arm down, which is a vote, or you put your arm up, which is a vote, right? So if you don't put your arm up, you're voting for the right one here, right? So first one is, if you put your hand up, you say, okay, what makes human real? You need to have at least 60% human body parts, yeah? So even if you have robot arms and robot legs, you know, you're still real, right? Or you need to have a conscious, yeah? Maybe you don't need even, you know, maybe you can have a fake arm, maybe you can have even a lot of fake stuff, but at the end, if you have a consciousness, that makes a human real. Okay, get the question? Let's vote. Who thinks what makes us real is that we have a lot of human body parts, at least 60%? Oh, so it's not about the human parts, it's only about the consciousness. Yeah. Interesting question. I would like to talk a bit about what is actually this AI? Is this holistic idea, or is it something else? And I would like to do another little test with you. Yeah? And I would like to do a little test, it's called the Turing test. And I don't know, who knows Turing? Alan Turing. Oh, this is good, this is perfect, we see it already. And where is he famous for? Sorry, for? I didn't hear that, sorry. Yeah, exactly, Turing machine. And what else? Enigma, exactly, and what else? He also had a test. What was the test about? Yeah, so there was a little test. Can you explain what it did? Did you have an idea? Exactly. So I will repeat it again. What it did actually is you had to communicate with something. You didn't know what it was. And based on the conversation, you had to sort of judge if it was a human or a machine. It's called the Turing test. And then you had to say, okay, nah, I don't think this is not a human, this is an AI, right? That was part of the test. But the thing was, you had to do it by text, because they always thought, you know, if you would hear it, you would know it immediately, right? And that's still used, by the way, right? It's still something that's live. So what I would like to do with you is, I would like to do a live Turing test. And I will let you listen to a voice, and I would like you to vote after a while, and you have to say, is this an AI, or is this a human? Yeah? So, please listen to it.
Hello, how are you today?
Okay, how are you?
Good. Well, I'm calling about an online request you once made about health insurance coverage. We work with all major companies and compare all the rates for you. I can get you a quote in about 5 minutes, okay?
Are you a robot?
I am a real person. Can you hear me okay?
I can hear you just fine, but you sound like a robot.
I understand. Can we continue?
Good. Who thinks she is an AI? Oh, exactly. Who thinks he's not an AI? Oh, she is not an AI, sorry. But she's human. Who thinks the story is completely different? I heard here, some people think here that he is the AI, right? So I will actually explain a bit of the background on this story. It's not just made up by me. It's actually something you will find in the news, and it's about Samantha West, is her name. She works for a company called Medicare. And there's a lot of stuff on the internet about this, because they tried to figure out actually what this voice was, because a lot of people were actually called by her, and people thought it was an AI, right? And this was actually a journalist calling that same number that he had to figure out if this was an AI or not. But the story seems to be a bit more complicated than this. It seems that the story is the following. And then you can judge if that's an AI or not. It seems that there is a person, in this case the guy, he calls a number, right? And it seems that what happens is his voice is translated into text. His text is translated into another language. And in the background, there's a sort of call center with people, and they press buttons on a soundboard as an answer. Yeah? So they actually have sound samples that leads to other text. The text is translated, and the translation goes through a voice synthesizer, and that's played back to the person. I have no idea if this is true, right? So if you want to read more about this, go to the internet to find Samantha West. But the question here is, if this would be true, you could say, yeah, but it's humans, you know, pressing buttons. Is it then an AI or not? It depends a bit how you look at AI, right? Because a lot of these components in there actually, you know, they are translating languages, they are recognizing text, yeah? So there are a lot of components actually used in this setup, which you can say, well, they are very smart, right? Maybe they're artificial intelligence. And that's actually how I look at AI, yeah? So AI is not this holistic idea of this person, you know, this woman sitting there that's being very smart, you know? It's actually a lot of components that need to work together, you know, to make this intelligence. And the interesting thing is, I know we are not there, you know, that everything is 100% mature, but there are a lot of components in there that are very mature, right? So if you look here on the left, you see the same one, speech to text, speech translation, text analysis. These kind of components are getting to a level that they are very mature, yeah? Which means you can already build and use these kind of AI components, you know, to make applications around and to use it, for example, for a chatbot, yeah? And over time, you will see that also all the other components will be developed and developed, which means that all these little building blocks will make things smarter. But you actually only need these kind of small components to actually build very smart things on, even self-driving cars. What's also interesting is actually the connection with the cloud, and I will come to that later, but a lot of these components are actually usable by you today, right away. You can now go to AWS, and you can actually start using some of these components on the platform already, put in your own text and you'll actually have the speech, yeah? Or you will have the translation. And you can actually use this also in your own applications already as well. Yeah? And you see some of the examples actually that I took here from AWS. Text to speech is one of the examples of the components actually on the cloud. And that means also if you want to build your own mobile application that talks to customers, you can actually also use these components, right? You can make a mobile app that talks to your customer as a bank, and then in the background, you actually do the voice recognition, you translate it, you use a sort of FAQ kind of backend, and you communicate it back, you know, by the speech, actually through the phone. Yeah. So you can actually already build these kind of intelligence cases. And actually, if you look around at banks and insurance companies, just as an example here, we see a lot of cases worldwide that are actually experimenting with AI. And these are some cases that you see for banks, yeah, around fraud, around advisory, chatbots, self-assistance, but you also see it in the context of insurers. So the question is, what can you actually already do with this AI today, right? What you can already do is you can predict demand. If you look at all the data flows, you can already predict where the demand will be for any sort of data that you're looking at. You can actually analyze performance or problems. You can discover insights or patterns. You think, hey, this pattern is normal, this pattern is not normal, right? You can also detect incidents or opportunities, or find people or content in that. You know, did you really specifically isolate someone in all the data flow that actually flows by? If you would extend that to data and to endpoints and to network and security, you can use this, right? If you have all the endpoints and you have the data flowing and you can actually analyze it like that, then you will be able to actually have these kind of cases. And we call that applied observability, right? A bit of the new trend that actually when you look at all these flows, you can actually put intelligence on top of that to analyze this. And these cases that I show here are not extensive cases. Maybe there are many more, you know, and maybe some of them are in development. But that means, for example, if you look at it from a security perspective, you can actually use it for detecting usage patterns, but also which patterns are not normal. I have a network. How does the communication normally flow? And then you see a different pattern. You know it's not a normal pattern. Yeah? You see users logging into applications. You know what normal patterns are and what not normal patterns are, right? So you see that you can apply AI also already in the context of these kind of cases as well. What's also important, if you talk about AI, that everything is connected, because you actually need to connect, you know, the intelligence with the data, right? So you need to make sure everything is connected, because the whole idea around this is that everything is connected. But of course, at the end, you need to transport always zeros and ones, right? Because everything we're doing in IT currently is with zeros and ones. And as you can see here, the answer to everything we're currently doing is zeros and ones, right? Don't know if you recognize this number for the people that are very good in binary numbers. No, it's 42. Connected smart machines are also an interesting concept, right? Because you can have a smart machine, you can have a robot, but what if you have multiple robots and these multiple robots can actually communicate with each other? Yeah? Let's say you have a drone, smart drone that can fly itself, you know, search around and stuff like that, but then you have 10 drones and they are aware of each other and they can actually coordinate with each other, right? And that's what you see here. We have different sort of drones. You can have like movers, or you can have robots, or like cars, but if you connect them, you can actually get a fleet or a flock, yeah? So this idea of a self-driving taxi, you can actually have a self-driving taxi fleet, yeah, that communicates with each other as well. And that's definitely the future if you look at this. Of course, we have a lot of promises also on AI, and some of them, you know, Tesla made already promises around the self-driving, you know, a car and 1 million robot taxis in 2020. I don't think we made that, right? But you see the new promise from this year. Now the expectation is, you know, in a couple of years, maybe we have some of the self-driving cars. What we know for sure, this will somewhere happen in the coming years. This also affects us on a daily basis, right? And the work we are doing. Because it means actually that you can use these kind of AIs already with all the existing tools and cameras and setups and data that we have already to connect data, maybe us personally, but also as a company. It means that you can isolate someone actually from a group of people, take that person out, And then actually based on the picture, you can say, hey, but this person with this Twitter account, hey, this person with this linked account is actually the same person. I can actually get that digital data together, I can analyze it, and I can do a lot of stuff with it, yeah? And one of the things I can do, for example, is analyze, what kind of person is this, yeah? You can even do an analysis on this person, yeah? So for example, is he competitive or not? Is he laid back or not? Yeah, based on the data that you actually published in these different channels. Can you imagine you're walking around the street and you have this kind of analysis that you can actually do in reality when you're walking around? And I'm not saying that we should do these kind of things, but from a technology standpoint, you see that we are able already to do these kind of things nowadays, right? And sometimes we can have a good case around it, but maybe also sometimes we need to protect that this actually happens from a privacy standpoint as well. By the way, this is not my profile. I'm not this guy at all, yeah? So just... It was actually someone real that I used for this, but I'm not going to mention who it was. So. The other part of the smart machine age, if you look at the technology, is not AI, but it's quantum. Yeah? And that's connected to this idea of unlimited computing power. And some people here in the room will think, what does it do? Does it really matter, a faster computer, I mean, okay, it's a bit faster, Every year it's a bit faster, right? Does it really change anything? I think it does. And the question is, why does it change anything, yeah? So what can we actually do with unlimited computing power? And then I'm talking about a combination of cloud and supercomputers and edge and quantum, yeah? When we talk about unlimited computer power, we often also talk about supercomputers and everything like that. And we have to understand when we had supercomputers in the old days, in 1969, I don't know, do we have anyone in the room that actually worked with supercomputers? No? Can you raise your hand if you actually did anything at that in the... Okay, well, you're probably otherwise close to it, right? But in that time, 1969, supercomputers, we thought they were very fast. They're actually slower now than your smartphone. Yeah, probably you have a newer phone than an iPhone 7. Supercomputers are slower than the smartphone in your pocket. At that time, we also didn't really realize what a supercomputer could do, right? I can even remember IBM said, 5 computers in the world should be good enough, right? They had no idea, of the real impact of computers. We had no idea of the real impact of supercomputers. We also, a lot of problems were not solved, We didn't really know what a mobile phone was. We didn't know what apps were. We didn't really know how to build applications. A lot of stuff was unknown. We had technical issues at that time. That is where we are today. We are back in 1969 and we're looking at quantum computers and we think, what is this thing? It looks a bit weird, with all these cables and stuff. It sounds very techy and we have no clue what we can actually do with it, right? That doesn't mean it's not going to happen. Yeah, and that's where we are now. We will develop these technologies over the coming years, and we can figure out actually what it can bring to us. And some of you are more in the networking space or in the connectivity on the cybersecurity space, and you think, okay, this is about quantum computers. What does it mean for me? It will relate to you as well. And I will try to give you some examples why this relates to you as well. First question when we talk about quantum computers is, why does it actually matter? Yeah, and for that it's good to step a little bit back and to think about, what kind of things can we actually do with mathematical models and with computers. And sometimes what we don't realize is that we actually have problems that we can't solve. Yeah? So for example, you already had a cup of coffee probably when you walked in. If you pour a bit of milk in it, there will be an effect, right, of the milk in the coffee and it stirs. We have no idea how to calculate that. Yeah, there's no mathematical model to actually deal with that. Another one, it's called the traveling salesman problem. Let's say you have 10 locations and you want to travel to all the locations once, but you can go every road only once. Yeah? How do you calculate that? You can calculate that, although it's a difficult thing to do. But what we can't do is verify that it's actually the shortest route. There is no way to verify the traveling salesman problem. There's no mathematical model that can actually deal with that. Yeah? You think, that's weird? No, it's true. Yeah? If you look at quantum computers, this is where quantum computers come in. They actually can solve some of the issues that we can't solve today in a different way of looking at it. I realize some of you, maybe today is the first time maybe you really heard about quantum computers and what it can actually mean. So I would like to do a crash course with you, yeah? And I think you can have a PhD on this. It takes you 5 years or so, and then probably, a couple of percentage on this topic, yeah? And I'm not going to say that I'm the real expert on this because this is really hard stuff. But what I will try to do is to make this 5-year PhD into a 3-minute version for you, okay? So I hope you will be a quantum expert when we walk out of the room here. Yeah, so please bear with me and see if you can follow this. So I call it the 3-minute quantum physics for CXOs. First thing I want to tell you is that if we talk about quantum computers, this is actually inspired on nature. Yeah, see it as a nature computer, right? So the stuff a quantum computer does actually already exists in reality, yeah? So nothing of this is made up. We try to copy things that actually already happen in physics, yeah? So in nature. So that's important to understand. And we try to use that smartness and we try to put it in a box and then try to use it as a computer, right? The first concept is superpositions. If you talk about quantum, you have to look at the bits. I said already, if you look at IT, everything is in zeros and ones, right? Even if you have an image or whatever, it's always zeros and ones. If you do a calculation with IT, that means you always calculate with zeros and ones, right? So can you imagine how many zeros and ones you need just for one little picture? Yeah. Quantum computers don't work like that. Quantum computers actually calculate with zeros and ones and every other value. Yeah. That means they can speed up enormously by calculating different sort of scenarios and stuff because they have actually a lot of values. They only need a couple of characters actually to do very complex calculations with. There's always a but though, and the but is you can't actually ask the computer what the bit value is. Yeah? So if you ask him, are you a 0 or 1 or what is your value? It will always say a 0 or a 1. Yeah? This is where it gets a bit hardcore, but that means quantum computers work with something that we call superpositions. Yeah. So I was calculating, I was actually very close to the 1 or very close to the 0. And to be actually able to figure out what the real position was, we use superpositions. Yeah. Difficult concept, but just remember zeros and ones and any other value can be used for calculations. Imagine the enormous computing power that you will have with that. The second concept is what we call quantum tunneling. That means if you have a bit, yeah, in quantums it's called a quantum bit, a qubit, and you spin up a bit, the qubit can actually move from one place to another. Yeah? So I can spin up a qubit here, and it can actually move to here. Yeah? And the interesting thing is, if there's something in between, it can actually travel through there. Yeah? Which is a bit difficult if you put it in a computer, because then it means if you put up a qubit in a computer, it goes out of the computer, right? That's why it looks so complex always, with a lot of cooling and stuff around it to keep it in a machine. But that's called quantum tunneling, yeah? The third concept is quantum entanglement. That means you can actually spin up a qubit, spin up another qubit, you can connect them with each other, and then something magic happens. What actually happens is this qubit will have the same value as this qubit, even if I move it apart from each other. And if I swap this one from 0 to 1, then this one will also automatically swap. Instantly, securely. Probably some of you didn't follow this, so I'm going to say it again. That means you can spin up a qubit, another qubit, you can entangle them, you can move them separately from each other, and they will stay the same value. Even if you swap one, the other one will swap as well. So you can also have like 50 qubits connected with each other and use that actually in the way you actually calculate. I was talking about I was talking about quantum and how it also affects us in our daily operation already. If you look at some of the things we are doing, for example, around security, we're actually relying on standards and protocols that are based on something, very difficult way of calculating something, but the reason why something is secure It's because we believe we can't really compute that fast that we can actually get the numbers out of the model that we use, right? So we encrypt something with a secret number. Yeah, I will not go into technical, but that secret number is difficult to calculate, takes a long time. But actually it looks like the way to decrypt it, it's called Shor's algorithm, is very effective with a quantum computer, which means it might be already today possible with the press of a button to use a quantum computer to decrypt anything you have encrypted today in real time, as well as all the data you have encrypted the last 50 years. This is not a theory, this is reality. And there are experts out there that actually think we already have these computers, yeah? Because quantum computers are in development, and probably this is also one of the cases that has the strongest quantum case currently. How do we solve that, by the way? Anyone, any idea on that? The way to solve it, as it looks like, is actually to use quantum computers to do the encryption itself. Yeah? They're called quantum encryption. And this is why I started this morning with, maybe this is the time where you look back at, hey, this is where I got this quantum ID. Probably if you start looking around you in the newspaper from today and tomorrow on, you will see a lot of stuff around this topic. You think, hey, they're talking about quantum already. Yeah? Did you actually see that there's an Eagle 1 rocket that will be launched soon into space that's going to distribute the keys for quantum encryption? Yeah. This stuff is going on already. Some of the other problems we can actually solve are very much connected to these SDGs, because what we actually learned so far is it looks like these quantum computers are very good in very complex multidimensional problems. Yeah? What is a complex multidimensional problem? For example, climate change. Yeah, because you need a lot of data and it all has effect on each other. You have different sort of scenario. These kind of models might be very good to actually to be running on quantum computers. Also stuff like food production, yeah, fertilizer production. These kind of things are extremely complex, and they even consume up, as you can see here, 2% of the world's energy is used by calculating the mix of for fertilizers. So that means we can probably use quantum computers for these SDGs to see how we can actually make cases that can help us. But of course, that's very difficult, because that means you start with this SDG, right, that I showed you in one of the first slides, but then you have to translate it into, okay, what is really the use case? Yeah? How can we actually use this in this context? You have to figure out how do we actually build an application. And then you actually have to program this on a quantum computer, right, which is a very hardcore work, and we have to build a lot of skills on this to actually make these kind of cases. And that means it starts on the left with all these SDGs, but on the right, it's hardcore implementation on circuits, on quantum computers, right? And all the disciplines in between are needed to understand, why is this important? Why can we use this? For which kind of context can we use it? But then at the end, also program it actually into these quantum computers. And these are some examples of potential use cases. But remember, we are 1969, so we have to figure out what the real use cases will be. But it looks like some of these use cases might actually be the cases that are very strong in this context. I'm not going in detail on this slide, but what you see here, this is a sort of view on where are we on quantum and where is it going. And you see also on the right here, quantum has a long road ahead, and CXOs need to be educated on this. Companies need to be educated on this. And that's also one of the reasons why I like to put this in a storyline like this, to put it on the agenda, to get you in on this, and to figure out together where this is going. This is a bit much, this slide, I know, but I just wanted to show you anyway. What you will see is, like I said before, you need people on the use cases side, you need people on the application side, and of course you need people that really do the hardcore technical parts, but we have to probably do it in the same time, and we have to build skills in these different disciplines at the same time. Europe, the EU, is also investing big time in this. There are big programs running in Horizon Europe, and they have billions of euros available. And they actually have a program, it's called Quantum Flagship. And as part of the Quantum Flagship, they actually sponsor technical university projects, implementations, collaborations between companies, for example, you together with us in some of the settings, potentially. But these kind of cases are actually funded by the EU. And as you see, statements like this, quantum computing is changing the future of IT as we know it. Yeah. There's one other little thing that I would like to talk about a bit as well, and that's one of the things. It's not related to quantum computers in itself, but is related to this idea of quantum networks. I was talking about this idea of this qubit, right? You could spin up a qubit and another qubit, and they are connected to each other. What would actually happen when you had a qubit and another qubit and you move them away from each other? Yeah? Let's say, if you look at Concha, we have a location in Ljubljana, we also have locations in Tromsø, which is in the far north of Norway. Let's say we put a qubit there and we put a qubit here in Ljubljana. Yeah, we are not in Ljubljana today, I know, but let's say that is an idea, right? And then flip the value of the qubit. Then actually the other qubit will flip at the same time. And this is called spooking action communication at a distance. And some people say, well, if this is true, then who was wrong? Albert. Exactly, and Albert was wrong. Yeah. Einstein was wrong, because then it will be faster than light. Another interesting concept is, if this is true, and this has already been proven that this works, then this is secure. You can't break the encryption between these two qubits. So the communication is completely quantum encrypted, impossible to break. Yeah. So this might be the new future of internet, and that's what we call it, quantum internet. Yeah? And even in the European programs I was talking about, there is money available to develop and continue development of all of this on all the different levels that I was talking about. Technical side, but also on the use cases side. Some people say, hey, but does that mean I still need a router? Yeah, do I still need network cables? Yes, you do. Because actually, the way they communicate, they don't need anything. Till a couple of kilometers. Because if you go further and further, you can do this up to 100 kilometers, but what you need then are, anyone, any idea? Repeaters, quantum repeaters, right? So we also have like infrastructure for that as well. And of course, when you start, these two qubits need to connect together, and then you need a physical connection between the two. Yeah. So that's, but it will look completely different. Technical University in Delft actually realized already the first quantum network based on this entanglement. And this is just a press release that I'm showing here, right? This is going on. The technical universities are doing implementations on these kind of networks to make this work. And this is how it looks like. And I would expect it to be a bit more fancy, right? This looks like 1969. But this is actually one of the quantum repeaters, yeah, you're looking at here in the experiment of the university in Delft. What you also see is stuff that we use daily, SSH, recent news, it's quantum secure now. How it will change the future of SSL. Yeah? Just some random articles, and you see even this is 2020, you know, some of them are already a couple of years old. This affects all of us already. If you want to experiment with it, you don't even have to wait for quantum computers, but you can already start learning what it actually means. And you can actually go to the cloud, to the hyperscalers, and start using these components. And you see some of them here. You see already on Amazon it's called Bracket. On Azure it's called the Quantum Cloud. It changed the word a bit. It was called Quantum Preview. It's called Quantum Now. But you can go there and actually spin up systems and do already simulations to learn how these circuits and stuff actually work. Yeah. So this is already going on. You can jump on it already. Do we have the real quantum computer yet? I don't think so. But maybe between 3 and 5 years, we might be having the first real launch on that. And that means if you look at the future IT landscape, it will change, right? So what you will see is, it will start with a purpose-driven organization. You will need enterprise agile teams. You, of course, you have application data, but it will run on a sort of cloud platform, which will be a combination of your traditional data center, the cloud, but of course you will also have these new components that will actually have some of the use cases in it. And so you will have traditional hardware, cloud, and quantum. So quantum will not replace some of the other ones, but of course will find its place into that as well. And of course, underneath, you need to make sure you also have a secure network to actually be able to link all of this together. So Concha NIL, as part of Concha, doesn't build quantum computers, right? But of course, we are very strong on cybersecurity, networks and cloud. So this is also very much in our focus, of course, to see how this develops and figure out, of course, also our position in this. But of course, being connected and being secure is one of the most important things actually to deal with. So you see here the Concha countries. It's a bit more darker blue. So we are in Slovenia, in Germany, the Netherlands. We are in 6 countries, also in the Nordics, but more familiar for you as NIL, as part of Concha. If you look at these technologies, you will see that we will change from the old agriculture age to the machine age and to the smart machine age, but we need to be able to trust technology. We need to be able to trust our networks, our connectivity, and we need to be strong on cybersecurity, because it will even be more complex than it was today. Hope I inspired you a bit on the quantum. I hope it wasn't too tough for you and that you were able to follow it. And thanks for listening to me, and have a great day.